Now we'll discuss the finite automata. So finite automata come in deterministic finite automata and non-deterministic finite automata, both of which can recognize the same set of regular languages. So we can define in that way finite automata come in DFA, means deterministic finite automata, and non-deterministic finite automata, and both of which can recognize the same set of regular language regular languages. So we'll discuss what is regular languages and so on later on, but now this is finite automata, and it come in two forms, either deterministic finite automata and non-deterministic finite automata. Now first we'll discuss the deterministic finite automata, its notation, its terminology. Then we'll discuss the non-deterministic finite automata. So now first, deterministic finite automata or DFA. So we can define that this deterministic finite automata is defined by using a 5-tuple. So definition, deterministic, a DFA is defined by 5-tuple. M, suppose the deterministic machine is M, is equal to Q sigma del Q0, Q0 and F. Now what are the symbols and their meanings? So Q is basically is a finite non-empty set of states, like Q0, Q1, suppose Q of n, suppose there are n number of states. Now this alphabet is a, we can define, is a finite non-empty set of input symbol. Set of input symbol, like suppose 0, 1, maybe A, B, etc. Now this we can define delta is basically defined in that way: Q cross Cartesian product to Q. It means it is a transition function, which is basically, it is a transition function, and the rule, which basically, it is basically a rule which helps to map between two set, is basically called the transition function. Means if you are in any of the state as mentioned here, Q0, Q0, Q1 to Qn, and your input symbol, either it may be 0 or 1, and you transition to another state, that is a Q. So it is a transition function. Now what is Q naught? Q naught, it basically belongs to Q. Q naught, so it basically is the initial state. So is the initial state. Initial state. And what is F? F is a subset of Q. Means is a set of final state. Final states. You know the terminology for the deterministic finite automata: Q, sigma, del, Q naught, and F. So in simple form, we can define a deterministic automata or deterministic finite automata is one in which each move, that is one state to another state, is uniquely determined by the current configuration. Now, what is Q cross sigma? As we have mentioned, that Q is, we can write in that way. Suppose we have it to set like this. Suppose here it is a Q naught and input symbol is 1. Suppose your input is, suppose Q2, your input is 0. All are this and this, and suppose this is another. It is a basically Q cross sigma, and it is suppose Q naught, it may be Q1, it may be Q2. Suppose by using this you may move to this Q0, or by using this you may suppose move to Q2, etc. So this is basically a transition function, that is Q cross sigma to Q. So the transition from one state to another state are basically governed by the transition function delta. So if suppose del Q naught comma A is equal to Q naught Q1, what is the meaning of this? What is the meaning of this? It means if the deterministic finite automata is in state Q0, Q naught, and the current input symbol is A, and then the deterministic finite automata will go into the Q1 state. Now, to visualize and to represent the finite automata, we use these transition graphs. And in transition graph, vertex basically represents the state and the edge basically represent the transitions. That is, if Q naught and Q1 are the states, internal states of some DFA, deterministic finite automata, suppose the machine is M, then the transition graph or graph, that is, it is a directed graph can be represented by using this. One of the state is Q naught, and as it is initial state, so there is an incoming arrow Q naught, and by taking A, your present input symbol is suppose A, and you will move to Q1 state. So this is basically a transition diagram corresponding to this transition function. So the initial state is basically identified by an incoming arrow with unlabeled. There is no label and not originating at any vertex. So this is an initial state. So it is an initial state, and final state are basically represented with a double circle. So final state is basically represented using the double circle. In that way, it is a final state. We can represent in that way. Now, uh, now a transition graph, as we have mentioned that a transition graph we can visualize by using the transition graph. So now a transition system uh, accept a string W, we assume that W is a string. So when it will accept a string, so we can define in that way a transition system. A transition system accept a string W, and which is basically in sigma star when if a there exists a path which originates from some initial state and goes along the arrow and terminate at some final state. Then we say that the string is accepted. That means when it reaches to the final state, the string will be exhausted. And the the path value obtained by concatenation of all edges or all labels edge labels of the path is equal to W. So this is the scenario when a transition system basically accepts any string W. So the automata or the description of the automata can be done by two ways. One is the transition diagram and another is the transition table. Uh, Transition table. Okay. Now, uh, what we have mentioned that uh, a description. So the description of automata, description of automata can be done by two ways. One is a transition diagram, and two, transition table, transition table. And this transition, what is transition table? Transition table is nothing but a listing of the delta function. So which is a tabular listing of delta function. So by using this any of this either transition diagram or transition table, we can describe an automata. Now I will give an example. Suppose uh, we have a transition diagram. Suppose we have a transition diagram like this. Suppose it is a Q naught and it is a Q2 and it is a Q1. This is, so this is an incoming arrow, initial state. Input is suppose 1 and it moves by using 0, and this is basically suppose your input is 1, here it is a 0 and input either 0 or 1. Now what is the transition table corresponding to this transition diagram? Transition diagram, so its transition table, so its transition table, but we can write in that way. It is as we have mentioned, that is a listing of the delta function, so we can write in that way delta, and your input symbols are either 0 or 1. So now you are in initial state, so Q naught, and by using 0 you can move to Q2 state, and by using 1 you can remain in the same state Q naught. Now if you are in Q1 state, by using uh, 0 you are in the Q1 state, and by 1 you are also in the same state Q1, and Q1 is a final state, that's why we have marked as a circle. In case of transition table we have marked as a single circle, and for Q naught you are by taking 0 Q2 and by taking 1 it will be Q1.